We have a very interesting and important video here. Good afternoon. Thank you for joining me. I am Mr. Ish. Redox reaction, half-cell reaction potentials, and the determination of a reaction to be either spontaneous or not spontaneous. With the removal of all confusion and difficulty with regards to this subject, I will make this so easy for you all that you should not have a problem with these type of questions after this video. I have selected here just a bunch of reactions with regards to metals from a activity series. Everything here is with regards to oxidation reactions. A similar table can be presented with everything, all these reactions flipped around with regards to reduction. You see, as you're going up over here, you're having an ease of oxidation. If everything was flipped around into reduction reactions, you would have ease of reduction as you go up. For each of these half reactions, I have the voltage or the potential written. Positive usually indicates something which will be spontaneous. Negative indicates something which will not be spontaneous. When you're looking at everything over here going upwards, you have alkali earth, transition metals, and you have a noble metal over here. You know, these are very reactive. As you get down and further here, you get less reactive. These would rather lose electrons and be oxidized because they can easily achieve that noble gas configuration. Metals such as these would rather gain electrons. It wouldn't matter because then it can help them achieve their outer shells with regards to their d orbitals, the d orbitals of transition metals. But anyhow, we should not get too technical over here and keep everything simple and to the point. When you're looking at a table like this, as you go upwards, these items would want to be oxidized, which means they would be good reducing agents. As you go down, these would prefer to be reduced, so they would be good oxidizing agents. Of course, what you're seeing here is an oxidation reaction. In reality, this would be better off in the flip reaction. If you flip any reactions around, then you have to change the signs of these potentials. The trick to doing these type of questions is always look at your reaction and separate the half reactions, and then look at the nature of the metals which are involved. If things are contrary to their nature, you'll have a not spontaneous reaction. If everything is proceeding with regards to the nature of that metal, everything will be spontaneous. Allow me to show you 4 examples to bring all of this into good perspective. I have a reaction over here, magnesium plus Fe2 plus, to give you magnesium cation and iron. These are non-ionic states, they're solid. The ionic states are aqueous. I'm not putting the S and the AQ, the solid and the aqueous designation, just for being a little expedited over here. When I'm looking at this, I'm looking at a half reaction, magnesium, to give you magnesium 2 plus and this. When I'm looking at the iron, I'm looking at iron being accepting electrons to be reduced. Here you're seeing magnesium is losing electrons, it's being oxidized. Here you're seeing iron is being reduced, it's gaining electrons. If something is higher on the table, it wants to be oxidized. If something is lower on the table, it wants to be reduced with comparison to something that's higher on the table. Magnesium is higher on the table, therefore iron should be reduced, magnesium should be oxidized, and that's exactly what we see over here. Magnesium is oxidized, iron is reduced. By the nature of this table, the reactivity goes upwards. Everything here is in a good manner. What would be the potential of this reaction? You know, magnesium is 2.36. Atom, always atom. Iron here is 0.44, but this is a oxidation reaction. Here we're seeing reduction reaction. It flips. So it flips to minus 0.44. Add these up. You'll have 2.36 minus 0.44. You'll have here 1.92 volts. And it's a positive value, so it would be spontaneous. And this reaction here would be good. It would occur as it's stated, a reaction that will occur. Let's look at this. Lead solid plus iron cation to give you lead cation and iron solid. Half reactions. Lead is undergoing an oxidation reaction. It's losing electrons. Iron over here is going a reduction reaction. It's gaining electrons, as you see over here. It's gaining electrons. Iron is higher on the activity series than lead. Therefore, you should be seeing oxidation as you go up. You should be seeing reduction as you go down. Technically, based on the reactivity of these two, iron should be oxidized, lead should be reduced. But we're seeing the exact opposite. Lead is being oxidized when in reality, compared to iron, it should be reduced. Iron is being reduced when in reality, with comparison to lead, it should be oxidized. Both of these reactions are contrary to the nature with regards to the comparison of the activity series of these both metals. Therefore, you will have a not spontaneous reaction. What will be the voltage of that reaction? Lead looks like this, exactly as you're seeing, it's 0.13. Iron looks like this, but it's supposedly in this form, a oxidation. Here we're seeing reduction. You have to flip the signs, minus 0.44. You have to add these two items. You'll get a minus 0.31 volts. It's a negative value. It will be not spontaneous. This reaction will not occur as it's written because the metals which are involved, especially iron, is working in a manner contrary to its nature with regards to something that should be less reactive. We have this magnesium solid reacting with silver cations to give you magnesium cation and silver solid. You have to analyze this. You can break out the half reactions. You have magnesium giving you the cation and 2 electrons. You have a balanced reaction here already provided. You have this with regards to silver. Based on the activity series, silver is lower than magnesium. Silver should be reduced, magnesium should be oxidized because the ease of oxidation is upwards for all the reactions that are presented here in terms of oxidation reactions. I'm seeing magnesium is being oxidized. It's with the nature of the metal that we're looking at, and silver here is being reduced, which is in the nature of what we're seeing here with regards to the trends. Everything here looks spontaneous, and it will be. Magnesium is an oxidation reaction. It has a potential here of 2.36. Silver here is a reduction reaction, but here it's oxidation. You flip it around to make it into a reduction reaction, and you have that. 2.36 plus 0.8 volts will give you the cell potential of this reaction. And the answer here would be 3.16 positive volts, and it would be a spontaneous reaction. Again, remember, the higher you are on the table, the metal should be oxidized. The lower you are with regards to something above it, it should be reduced, and that's exactly what you see here. As our last question, we have this lithium ion reacting with silver solid to give you silver ion and lithium solid. Break these into their half reactions. You have lithium ion reacting with an electron to make it a solid. You have silver, which is being converted into a cation with the loss of an electron. When you're looking at this series over here, which is just an abridged version of the entire large series, I just plucked out several metals. When you're looking at this series over here, silver is low, it should prefer to be reduced. Lithium is high, it should prefer to be oxidized because it can just lose 1 electron. Remember, lithium has an atomic number of 3. When you're looking at it, you have 1s2 and 2s1 in terms of its electron configuration. If you were to lose this 1 electron, it would become 1s2, it would become equivalent to helium, and it would become a noble gas configuration, and that would be more stable. And that's exactly why lithium should be preferred to be oxidized, not reduced. Lithium does not want to gain another electron, it would rather reduce an electron. And here we're seeing the exact opposite. Something which should be oxidized is being reduced. Something which is here, which should preferably be reduced with regards to something more active above it, is being oxidized. Everything here is contrary to the nature of those metals, and you will see a not spontaneous reaction. When you're looking here at lithium, the cell potential here for an oxidation is 3.05, but here for the reduction will be minus 3.05. For silver, the cell potential for an oxidation reaction is a minus 0.8, which is exactly what you have. Just add these and you'll have minus 3.85 volts. A very large negative value will be not spontaneous. Remember, this is a very large negative value simply because looking at items from the ends of the table, something which is very freely oxidized versus something which should be not oxidized, and you're having the exact contrary effects with regards to the half cell reactions. Keep in mind, again for the last time, as you go up on the table, for a series of reactions that are presented in terms of oxidation, everything is easier. In terms of oxidation, you want to have oxidation reactions. As you go below on that table, you want to see reduction reactions. If everything here was presented in the flip format for a reduction activity series, you'd have ease of reduction going upwards. These items would be up and those items would be down. These signs here would be all replaced. In that case, for that type of a table, you'd have reactions on the top which would prefer to be reduced, and the reactions on the bottom would be those which would prefer to be oxidized. These are the nuances you have to keep in mind. But everything here stems from the interplay between the oxidation and the reduction reaction. The item that's being oxidized, if it is actually being oxidized versus the item that is preferred to be reduced and it is actually being reduced, will give a spontaneous reaction. Anything contrary to that, you'll have a not spontaneous reaction and a reaction will not occur. Thank you for watching.